Welcome everyone to this next in the series of the SCF webinar series. Today we're going to be taking a look at the topic of millimeter wave, and many of you I'm sure will remember that millimeter wave has been standardized in 5G for a number of years now. And I guess as a result principally of the debates or interest in the mid-band spectrum, so the 3.x gigahertz spectrum, a number of markets have chosen to prioritize that mid-band over millimeter wave. But actually, we're now seeing, we had an interesting webinar last year on market trends. And for those who tuned into that, you will have heard that millimeter wave was growing in interest. And that kicked off a number of conversations within the forum. We learned that a number of the product developers in the forum were working on solutions and could see it themselves see an uptick in the market. And that initiated an activity which you're going to hear about today on this webinar. A number of the team who have contributed to developing a paper and are contributing to this webinar today are going to speak, and you will learn more about millimeter wave, and that will, I'm sure, be a very interesting session for you. So you can see the agenda on the screen. We will start with an introduction to the paper from Vicky, who led the development of the paper. And then we'll go into a number of presentations or little vignettes into some of the technology domains that are of interest in millimeter wave and the challenges that emerge from members of the SCF, TMYTEK, Microamp, DenseAir. And then we'll have a chance for a Q&A at the end, 10 minutes. We won't take questions during the webinar. What we'll do is, if you please type into the Q&A box, which you will see on the Zoom application, please type questions in there, and we'll pick up those questions at the end in the last 10 minutes of the webinar. Okay, so without further ado, let me pass over to Vicky Messer from Picocom, who's going to take you through the first stage of this webinar. Over to you, Vicky.
Thank you, Simon. So I'm Vicky Messer, VP of Product Management at Picocom. I'm an FCF board member and lead on this paper. Next slide, please. So there's a link to the millimeter wave paper, SCF 253, at the top here. The paper was launched during Small Cell World Summit in April 2020. This year, and we actually, during the event, we had a panel session which focused mainly on use cases and less so on the technology side, and we had panelists from BT, Icana, and I was on the panel as well, along with Simon. So this webinar gives an opportunity to do more of a deep dive, looking at case studies, products, and the technology perspective of the paper from additional contributors, TMYTEK, Microamp and DenseAir. So the paper can be downloaded from the SCF website, and I encourage you to read it for more details. Next slide, please. So as Simon said, the 2023 market status report, which comes out from Small Cell Forum, showed an uptick in the sort of planned deployments of millimeter wave small cells. We saw in the new data for 2024, which will be published next month, that there has been a bit of a slowdown on that, and we discussed that in the paper. But what is sort of seen clear an agreement across the industry and through analysts is the clear use cases and the timelines for those use cases. So we're seeing very much short term is more fixed wireless access deployments. This is providing maybe for rural areas where there's not a fibre infrastructure. There's interest and trials going on for sort of enterprise and particularly industry deployments, and we see that this has the benefit of the sort of the higher throughputs and bandwidth and low latency of mmWave. There's also been, particularly in the US, there's been a deployments of mmWave in sort of more mobile networks, and we're seeing that as maybe taking longer for deployments and when capacity is required. So there's definitely some analysis on what's been done to date on that within the paper. Next slide, please. So during the paper and the work discussions, we looked at the industry standards, including through Jack at Qualcomm was looking at this, particularly around O-RAN Alliance as well, and just looking at the release 17 3GPP specs, the FR2 or mmWave standards are split into two different frequency groups. So there's FR2 -2, which is up to 52 gigahertz. And then there's some new spectrum, which is assigned more for unlicensed spectrum at the higher frequencies. And in terms of the Small Cell Forum standards, this is Small Cell Forum developed the FAPI specs, and we've done some deep dive into what standards are applicable for mmWave and also which are applicable for different architecture splits, as shown on the bottom right of the diagram. So there's different splits of architectures, whether it's more of an integrated small cell or goes with a 7.2 RU unit. In terms of the technology that we're going to go into, it's really quite agnostic to what split is required. I'll go into that in a little bit more detail on the next slide, please. So in the paper, we talk about this block diagram. This block diagram was originally developed for FR1 and it's been extended for FR2. So on the right-hand side, you can see the mmWave module, which has the key differences compared to FR1 in terms of you need to convert the baseband signal either as an analog baseband or an IF baseband using an up converter, and then there's some beamforming ICs, and then there's the antenna, and we're going to have more information about that, particularly in the next presentation from Jack Rose. And also highlighted are the SCF standards used for data and control, including P19 that's used to control the beamforming antenna, which has to be quite a fast response. So this is a new standard that was developed particularly for mmWave for 5G. So next slide. So now I'm going to pass you over to Jack Rose, who from TMYTEK, who's going to talk a bit more about the mmWave antenna technology.
Yep. Thank you, Vicky. Hello, everyone. This is Jack Rose from TMYTEK. I'm solution architect and business development dedicated for phased array antenna. So a little briefing about the TMYTEK. TMYTEK is a world-leading mmWave phased array antenna total solution provider. So we capable from design and the testing the phased array solution, And we fortunately we are located in Taiwan, so we are very rich for supply chain ecosystem, help us to bring the product to the market in a very fast delivery time. And we will also, with the very resilient business model, we can capable doing the module customization and also some system integration. And thank you for Vicky's introduction. So today I will present our phase array antenna technology. Yeah. So next slide, please. So this high-level architecture of the phase array antenna architecture. So in the middle one, you can see this whole we call the phase array. So from the left side, that is have a IF signal that connect with the baseband, the FIC. So we up the sub-gigahertz band frequency to the mmWave band through the frequency converter. And when the frequency up to the mmWave band, so we have a beamformer matrix. So in this matrix is a PA, LNA, etc. So it's a matrix here. So in the right hand side, so we have a phase array antenna. So usually we design as a dual polarization. So because it's a more suitable for the different kind of use case. So and this is the hardware part. So the more important is we need to have a beam controller. So we need to have integrate with the baseband system to communication with the baseband to know how where the direction our beam should be point to. And when we receive up the message through the P19 that Vicky just mentioned, so we will run the beamforming algorithm to have precisely direction up to the antenna array and aim to the precisely to the mobile UEs. So this is a high level phase array architecture that TMYTEK to provide a whole this system. So you can see the beamforming array is a very compact the architecture here. So that's what and due to different use case and user scenario, they use a different size of array. So next slide, please. So the TMYTEK we have innovated the architecture we call the club cell. So we separate the beamforming array antenna into different layer architecture. So from the left-hand side, we call a layer 1. So this is a club cell. You can see that that look like the 4-leaf clover. So that's why we name this one of a club cell. So this club cell is our unit cell. We can build this by with the PCB and also the LTCC material. And we tie up this small piece of a club cell to has a 8x8 element. We call this a subarray. And this subarray is it contains all the high frequency material here and also up-down converter here. So it's a very very compressed module design that will minimize the design getting from the ODMs. And we use this subarray to again tie up into a antenna subsystem. You can see that the right hand side is our we demonstrate this structure demo set. So we can see that we have a L1 club cell, L2 subarray, and the use subarray to tie up the bigger array. And this array can be any size of array, just depends on your use case. And I will briefly use the functionality of these layers. So next slide, please. So you can see here, we see that the crop cell that dedicated, it have a antenna. We build in the beamforming IC and with antenna. So it can be a 2x2 or 2x4 antenna array. And in this small size of we call the antenna impact chip. So you build in a phase shifter and also the amplifier. And the 8x8 array is a cloud cell cluster. So we tie up many pieces of cloud cell into a larger array, and also, of course, generate higher ERP. And also, up-down converter also designed in this array. And also, we designed a digital and analog interface all on this module. So this module is that's I mentioned. We contain all the high frequency and the most complicated design within this module. So the ODMs and another ecosystem partner, they can use our subarray and build on their system board. So this system board is purpose to mount our subarray with different use case design. For example, you need a multi-beam, you need a MIMO, so you need to design the multi-pace of the IF pace. And also this board will in charge of power and some system control. And the most important is this board is contain FPGA being, I call it FPGA being executed. So in this design, just in charge of a communication with a baseband, and it's a command interpreter and also dispatch. So you receive a command and send a command to our phase array. So we can set the frequency, set the gain, set the pin control, and set different pin ID, etc. So it forms the whole entirely complete system here. So this is our fully architecture. So in the layer 1, layer 2, you can see that's we standardize these two layers and optimize the performance on these two. So it can have an economy of scale. So it can have very piece just like a chip as a cloud cell. So it can have an economy scale. So we can deliver this L1, L2 to ODMs. They can easily to build a system board. System board is just a low frequency board. It can have a low cost and also can speed up the design. Yeah, so this is our architecture. So next time we go in deep for our craft cell design. Lego piece, next slide, please. So you can see this piece. We here show our two Lego brick. So the left hand side we have 28 gigahertz. Is 2x2, and you can see the size very small. And we design a horizontal or vertical polarization. Also, we have another version for 45-degree polarization. And you can see the beam pattern here, very uniform. And left-hand side, you can see we tie up at 16 pieces of this Lego brick as an 8x8 subarray element. And you can see that its scan angle is horizontal is a 16 degree, and the vertical is also 16 degree. And compared to the right-hand side, we have another version of the 2x4 cloud cell. Because this design is we wire one pass to two antenna array. So you can see that the scan angle layer for horizontal is still 16 degree, but for vertical is only 30 degree. So these two different design is we can go for different use case. For example, for the left hand side, we have a uniform scan angle. So maybe you can use to checking the mobility indoor or that very cloudy UV environment. For right hand side, we only need a little tail because it may be used for fixed wireless access. We don't need to checking too much UE, and more than that, with just a little tile to aim to different UE in the long range and the short range. So next slide, please. So that we mentioned about that our cloud cell in cell, we have a fully calibrate that, and we know that the mmWave calibration takes so very long time. So this is our in-house event. We call S-Spin. It can have a very quickly OTA calibration. So we have a 2D and 3D. So it means we can test the beam in 2D, or we can measure a beam in 3D just within the 10 seconds. We know that the testing cost consuming up to 60 or 70 cost of a whole antenna array. It is very high percentage. That's why we need to a very fast OTA calibration to deal with to lower the mmWave phase antenna to the market. So next slide, please. And during the mass production, yeah, we also control the analysis and the quality. We measure different kind of the difference of a chip, and we separate the different beams by the beamformer characteristic, so we can improve in the overall production year. So we use the AI technology to help us to identify different beam characteristic. So next slide, please. So this is our FPGA architecture. You can see the middle one is that we dedicate developing this FPGA functionality. We have modularized about this the module. So from no matter what's the baseband is a different kind of baseband. We just uniform the just we mentioned about we adapt the P19 FAPI standard, so we can agnostic connected different kind of baseband platform, and also we can have a interpret to the command and send the command to the different modules to control the AIP beam, to set the frequency, to different some configuration. So from the phase array side, we can also adapt different kind of phase array. Even we can adapt the different kind of beamforming IC, because that's a uniform. Our FPGA have already modularized. We can adapt different kind of library to control different kind of beamforming IC, then connect the different kind of baseband. Yeah. So next slide, please. So these are our beamforming capability. We can have a narrow beam and a broad beam. A narrow beam, we can know it can reduce the interference. That's of course. And the broad beam, that's because on our beamforming algorithm, the broad beam can benefit for energy efficiency. Also for the baseband side, it can also wire coverage to cover the wire UEs. So we can see the use case. Next slide, please. Now we talking more about a fixed wireless access. So that's a very mmWave solution, very good adapt into this use case, because the market needs they need to improve the user experience. So they need to lower the loading of a micro station and dedicate for fixed wireless access. And challenge, of course, is the high throughput and the coverage. That benefit for a mmWave solution. We can have a spectrum availability and a wire bandwidth, and also it can benefit the advanced beamforming technology. We can have adaptive hybrid beamforming, and also if we can involve AI, we can have getting the more power efficiency, and as well as optimize network the optimization. So I think the David from Microamp, he can introduce more his product and also different kind of use case. Thank you.
Thank you, Jack, for the introduction. It's great to be here. I'm David. I'm a CEO and co-founder at Microamp Solutions. Next slide, please. As we all mentioned in the white paper that was referred by Vicky, at the moment there is an enormous need for providing capacity for different segments that can utilize 5G millimeter wave technology. And Microamp responds to this need, creating multi-gigabit and ultra-low latency 5G millimeter wave networks based on our purpose-built radios. So Microamp owns the 5G millimeter wave technology that is insourced in our radio portfolio. However, we provide end-to-end solution to customers, starting from the small starter kit up to the largest networks. Next slide, please. End-to-end solution is based on the radios we have. At the moment, we are able to provide 800 megahertz of spectrum with a 7.2 split. However, we are working on split 2 and split 0 that will be available soon. However, we want to make millimeter wave available for everyone, no matter whether it's a big mobile network operators or a small enterprise or system integrators or governments. That's why we created something like a 5G millimeter wave starter kit. It is the small network consisted of 3 radio units, server infrastructures, and the CPE that we are providing as well. So the customers can go to our website, request a starter kit, and assuming that they will have access to the spectrum, they can test a millimeter wave network in very friendly environment and show the values. Because millimeter wave gives a lot of, let's say, flexibility in terms of building the infrastructure and building the networks. And if we combine certain features of millimeter wave, we can really build the wireless connectivity adjusted for certain needs. For example, integrated access and backhaul feature that differs our solutions on the market can help to build very, let's say, cost efficient or in very good economics, the fixed wireless access that can be targeted not only to provide internet to homes, but also to connect public entities like hospitals, prisons, and government buildings and other institutions with the wide broadband. Another stuff is the mobility mode that we are the company, and at the moment I think there is a move on the market to enable mobility mode with the millimeter waves. We call it semi-mobility mode because it's up to 30-40 kilometers per hour, but it is more than enough to serve let's say people or citizens in the very dense urban areas. Another feature that can be deployed with millimeter waves and that shows the real value coming from millimeter wave is uplink heavy systems. With millimeter wave, we have enough spectrum to create both downlink and uplink systems. So Microamp can provide 70% in terms of the uplink, and it is very feasible in many applications, especially driven by the AI and AI video analytics or reasoning, where we are connecting a lot of data from different sensors. Very often we have camera sensors there and analyzing this in the real time. So this is the product that is scalable and that allows everyone to start deal with millimeter wave technology. Next slide, please. So here is the photo of the starter kit. So it is from the indoor testing that the results we put in the reports. So we use Druid core as a core network for this setup, DU, CU, and radio units plus CPE. So the size of the starter kit is not too big. It means that we can easily go with some partners like university to deploy it in their lab and to see what use cases we can build on this. We can go for the POC for the mobile network operators and test the outdoor solution, because the all vRAN or core network can be accelerated also in the cloud with this kind of things. And it allows us to test not only the wireless connectivity, which is the throughput or latency, but other features. So the distributed architecture that we have allows us, for example, to test integrated access and backhaul and deploy it by local authorities and internet service providers, for example, and adjust the fixed wireless access architecture to their needs, to their, let's say, use case or applications. The next slide, please. So this is the photo that came from the Druid Remis platform. So we were able to achieve 2 gigabits per second in terms of the capacity with the G-Node B attached. So this kind of throughput, it gives you good opportunity to steer or to adjust whether you want to have uplink heavy system or whether you want to have downlink heavy system. And this capacity allows you to deploy many bandwidth hungry applications related with the cameras, mostly when you have city center of New York, for example, and want to deploy 10, 20 cameras on the certain area as a first responder, for example. So this solution with 1, 2 G-Node B can serve you very quickly, and adjusting our system for uplink heavy allows you to transmit a lot of data in real time without compression, without buffering, and analyze it and then make some decisions. Next slide, please. And yeah, the first use case I want to mention is fixed wireless access is very obvious use case for millimeter wave, very easy to monetize and prove on the financial stuff. However, the whole industry is working to improve this use case, to go down with the costs of the deployment, improve reliability, and improve the, let's say, the quality of deployments. So the deal breaker here is integrated access and backhaul. That's really can, it is the first step of creating the mesh networks with millimeter wave, which is very much promising. And integrated access and backhaul allows you to deploy fixed wireless access in the places where putting fiber is impossible or it is too expensive. And this solution can find its applications not only to provide internet to homes, but many other even industrial applications that we are able to provide high broadband or create data links on the distance that previously was impossible. Next slide, please. And of course, private network market. This is the very promising sector for millimeter waves, because millimeter wave can bring a lot of value for certain niches at the moment for each vertical, I guess, because the flexibility that we are building the millimeter wave networks allows us to combine millimeter wave technology with really fledgling technology at the moment driven by the AI. So for many such applications that we have very advanced models, algorithms to analyze the data in real time and especially help us to make decisions. Combining this with really high throughput, simple system gives us enormous opportunities for a variety of applications, starting from the industrial cases, but also it creates a very interesting offer for governments and public institutions that they can create independent network, sometimes that can play as a critical one to serve very special purpose-built use cases. And if we want to create the capacity on some levels and enables new technology like AR, VR, or AI to analyze the data, mmWave seems to be the best, and it is the best solution to choose for the customers. Next slide, please. And of course, the public networks. This sector is driven by mobile network operators that we all know that in some time the sub-6 FR1 networks will saturate in terms of the capacity, and the multiplication generates a lot of costs. So there is evidence that we need to go with the higher frequency, with the higher capacity. And this capacity driven by mmWave can provide citizens access to the broadband internet, the symmetrical link in the most dense areas like city center of Tokyo, New York, or Delhi. And in that kind of architectures, at the moment, we still have high density of sub-6 radios, sub-6 base stations. So mmWave can only upgrade this network, do not complicate the deployments, do not add more density in terms of the radios, because in London or in New York, we have each 300, each 500 meters, the sub-6 network. So this is necessary for mmWave to works. And also the whole industry, I think all of the companies here, we are working to create new economics of scale or mmWave. So we want that this technology to be deployed in a very, very good economics, so that the return of investment for mobile network operators should be appropriate. However, we see that maybe this is the time for mmWaves, because the interest that came from many mobile network operators increased this year. So we do not have only the key like it was 2-3 years ago, but many mobile network operators see directly the need for deploying such systems. So we are improving the whole ecosystem, and I hope that also the CPE UE ecosystem device market will improve, starting from the industry up to the mobile network operators. So next slide, please. So thank you very much. That's all from my side. And now Lorraine Fearn from DenseAir will continue the presentation. Thank you very much.
Good morning and good afternoon, depending on where you are in the world. My name's Lorraine Fearn. I work for DenseAir. I'm the RAN architect there. DenseAir is involved in small cell and neutral host solutions and in developing them. Next slide, please. So I'm going to be talking about using mmWave for crosshaul. In particular, you can be used for split 0, which is backhaul, split 2, which is between the CU and DU, and split 6, which is between the DU and RU. The benefit of using mmWave for crosshaul is obviously that you don't need fiber at every location. Particularly if you're using it for backhaul, you can either have a series of hops between node Bs, or you can have it in a mesh system, and then you can just have one node B that is actually has fiber connected and goes into either the data center or the cloud or your network, whichever you need. Using it for split 6, obviously you can have multiple RUs per DU without the need to connect fiber between them constantly. The architecture will depend on what type of cross-haul you're using the mmWave for. But as I said before, in most cases, if you're using it for backhaul, you are pretty much always going to need fiber at the end point, you know, from at least one node B. Next slide, please. So DenseAir itself, we have had a couple of networks that we have deployed using mmWave to test. They're completely different networks in completely different parts of the country. One tested mmWave for front haul, and the other one tested mmWave for backhaul. We were very lucky in that we had absolutely glorious weather conditions for both systems, so it's worth bearing in mind when we look at the results, because obviously if it was raining, I think they would have been a little bit different. So the front haul, we achieved 1.3 to 1.7 gigabits per second. So that was only 1 DU and 1 RU. So we didn't try multiple RUs on the front haul. It was literally just one-to-one mapping. If I look at this photo here, this is actually the split 6 system. The mmWave is contained within that unit between the RU and the DU. And you can see the kind of weather we had. For the backhaul, we got achieved results of 0.8 to 1.7 gigabits per second. We got a lower result on the backhaul for of 0.8 because we did have some interference on channel 5 mmWave. So that 0.8 was only seen on channel 5. Unfortunately, we weren't able to access the interferer to be able to switch it off to see what it could have been like. It's also worth pointing out that the mmWave was an independent unit on the backhaul. It wasn't integrated into the unit. It was a separate unit attached to it. Next slide, please. So looking at it, we had a few sort of findings that from the tests that we want to highlight. Line of sight is key. We did find that, you know, as branches grew and sort of interfered with the signal, we did get a lot of flapping on the link, and sometimes it just cut out completely. So it's worth bearing in mind, you know, if you're planning to use mmWave, that you do have to consider the line of sight very, very carefully. And it's not just foliage. If you're in a city centre or something like that, you've got to think about big vehicles travelling down roads. You know, they will interfere with it. So it needs to be carefully thought about. We did find, as expected, that the shorter links did perform better than the longer links. I think that is to be expected. I mean, we didn't do huge long links. They weren't kilometres long. So we had the shortest link was 167 metres and the longest one was 413. So it's important to note that we didn't test great long links. We did do a comparative test with the backhaul with fibre. We did find that it was, we had a reduction in throughput of roughly 10%. But we think, you know, it's attributed to the occasional packet loss on the backhaul. There was no reduction observed for split 6 because the mmWave packet loss is compensated for by the HARC mechanism within the system. It's also worth noting as well on the backhaul that we weren't sure, we couldn't ascertain whether the reduction in the throughput was due to the test software we were using, because we were using iPerf, and we found that as we added more streams to the iPerf, the difference between the fibre and the mmWave reduced. So there was some thought that maybe it was the way the iPerf was processing it, but we couldn't get to the bottom of that. So it's, again, worth bearing in mind. The other things we found, what the backhaul, it had low latency sensitivity, so it was good to use. We think we can use it up to 10 hops, although we only tested it up to 3 hops. So we think that you could use it for up to 10 hops. You do need to do channel planning, because obviously as the propagation increases, the chances of interference between each of the units increases. So it's worth spending some time doing some channel planning. For the front haul, split 6, there is increased latency sensitivity. So depending on which standard you're using, depends on whether you can use 1 or 2 hops or maybe more. Again, if you're using 802.11ay, we think you can probably use up to 10 hops, but again, it hasn't been tested. So yeah, the effective latency from the multi-hops is it can affect this. It's basically down to the HARC IDs being used. So if it gets to the stage where there's no acknowledgement of the HARC ID, then obviously it doesn't get released back into the pool. So you can run out of HARC IDs, and that then affects the throughput. So that's the latency sensitive part of it, and that's how it affects it. But again, you can use that can be mitigated using a specific TDD mmWave unit. So yes. Next slide, please. I think that's it. Yes, so I'm going to hand back to Simon for a question and answer panel.
Excellent. Excellent. Thank you, Lorraine. That's been a nice tutorial from everyone there, going into a little bit more detail on some critical components of mmWave systems, and also some real world experience from trialing, which is food for thought, I think. Now I'm just before I ask the questions I have, I'm just going to check to see on the Q&A whether we have any questions. I can see everyone's rejoining me on the screen. Great. So we have one question coming from Philippe, which is it's actually directed to you, David. So you may wish to take this one, but it will be open to others to answer if they have views as well. So this is, I think, to some extent, David, you answered this, but let's just explore this a little bit further. It seems that private networks will benefit from mmWave sooner rather than later. Are there some specific use cases? I'm going to say specific because I know you talked generally about use cases, David. So if there's some particular ones that you're latching onto as seeing particular use cases in the market that are specifically going to really take off or really benefit from mmWave, and when will they be deployed? So if you could have a think on that one, David, and let us know your thoughts, that would be appreciated.
Thank you for this question. Very good. So private networks benefiting now from mmWave. So now it is the time, and now this let's say magic is going on. And in terms of the use cases, there is one specific area that with use cases that requires capacity, and these use cases are related with the cameras, or we call it camera sensor, that you have, or you need to have several cameras from different angles that are uploading the data or sending the data from cameras to the local server. And the main driver for this one at the moment is AI or some models, video recognition, all of this segment of software that analyze the data and giving us the feedback, no matter whether it is the reasoning, where you combine predictive maintenance with making the decisions, or recognizing something. We have a variety of such things. But the fact is that to make this application able to be deployed, you need to have real capacity. And sometimes you need to have symmetrical link or uplink heavy link. And millimeter wave is perfect because imagine you are using, or you got the spectrum for 400 megahertz. You have 300 megahertz uplink, 100 megahertz downlink, and it's the perfect because you can have several cameras in some areas. And imagine that some securities like police or medical healthcare, they are creating the millimeter wave bubble and doing something with the cameras. So on the some 100 square meters, something like this. So millimeter wave is perfect for this. Another sector is remote controlling. If we want to have or make remote controlling fully autonomous, we need to mitigate all the environmental risks that something is going on around the port crane or excavator or something like this. In this area, the controlling can be done through sub-6, for example, different network, but still you need to have a lot of cameras and machine learning, computer vision, so that the excavator, for example, can see what's going around and sending the data. It is maybe not critical for autonomous car, but if you want to make autonomous public transport, that the bus is following the same line, this is the critical. And then the video needs to be uploaded in the real time to the main, let's say, base to be analyzed. And remote controlling and autonomous, this is the second segment that is deploying now. Because healthcare, we have some POCs, it is booting, but cameras and remote controlling, this is happening now.
And that's very useful. Thanks, David. Is there particular markets? I mean, when I say markets, I mean like in regions where you're seeing the greatest interest, Europe, Middle East, US, where do you see those particular upticks?
So in Europe, I think Germany, it is the, let's say, key thing because they have open spectrum.
Yeah.
So many system integrators or many industries do not have spectrum issue. They are free to, let's say, consider whether this solution is feasible for them. And they are analyzing and they see, yes, we can try because there is no showstopper. There is no the issue that they need to wait, for example, 2 months for something. So Europe, also Asia Pacific countries like Indonesia, Philippines, they are trying to deploy fixed wireless access plus private networks with the same frequency, with the same infrastructure, that through fixed wireless access, they are providing high broadband, and with the same technology, they are opening the private network for the specific use case.
I think that's really interesting because so a hobby horse of the forum, the SCF, is the access to spectrum. I know that a lot traditionally the SCF has been very focused on mobile operator use cases for deployment of small cell systems. In past years, but we're very much seeing this growth in private network users, and you used a key term there, open spectrum, open access, and that's creating the innovation. My feeling is, my sense is that we're getting to the right sort of price points where it's worth experimenting with the equipment, and you're seeing industries, vertical sectors, taking the lead with their deployments. Is very interesting. Lorraine, I know that you participate a bit in our regulation and policy group in the forum. What's your view on the sort of open access spectrum as a sensible way to go with the sort of millimeter wave bands more widely, to see if it's possible to not get locked into a exclusive ownership of bits of millimeter wave spectrum? Would that be a sensible direction of travel to help this market continue to grow?
Yeah, I think so. I think certainly looking at neutral host vendors and anything other than the big MNOs, who are the only ones that really have the money to be buying licensed spectrum. If we're serious about opening the market up to the small cells and smaller companies, then it is the only way to go. Obviously, you need to sort of have some kind of control over it, otherwise we'll all be interfering with each other. But
I was going to say that
yeah,
I guess I mean that's the lesson learned from your trial. Actually, there was an
yes,
interferer, which is
yes,
interesting, is it? So you do need to mitigate against that possible scenario
absolutely,
where
absolutely,
interferers,
and it might not even be intentional.
yeah,
Certainly from my time in MNOs, I know that things like ovens can interfere. Something that's completely non-radio related. So there still needs to be some kind of control over who uses what and where. But I do think it needs to be a lot more open than it is.
Yes, thank you. So I'm conscious that we're running tight on time, but questions are now coming in. So we could go on, but we will be hard stopping at 1:30. So I'm going to pick up these questions quickly just to see. There's one question coming in on millimeter wave power consumption. I don't know whether anyone has any observations on the power consumption concerns or not. Compared to other connectivity solutions and other bands. And anyone got any thoughts on that?
I think the power consumption issue is truly the critical in mmWave band because the it's an array antenna. Yeah, so I can show everybody here.
Yeah.
So this 8 by 8 phased array antenna, and you can imagine that this tiny piece array can generate 50 it's 650 dBm ERP. So you can see that a very amazing technology here, but it indeed consumes the electrical power. But compared to the FR1, if we calculate the per watt vs per bit per second, I think mmWave band should be more we call the power efficiency compared to sub-gigahertz band because it can transmit very high throughput in very short milliseconds. So I think in this perspective, I think the mmWave band can benefit for the high throughput bandwidth or low latency as well as the power consumption. We call the power efficiency. Yeah, so that's
Lovely. Lovely. Thank you very much. And Vicky, to give you a chance to speak at the end of this panel, as you did a lot of heavy lifting on the paper development, I give you the honour of the last question. And it may be up your street. There's a question here about are there any plans to complete IoT with major software vendors? Now, I'm not sure who they're referring to directly, but in terms of software support for these systems, a lot of what we talked about, I guess, to some extent, has been sort of hardware platforms. We do have some major software vendors that are part or members of the forum, and I know that they are talking with a lot of the people speaking here today. But Vicky, is there anything you say on that about systems and software ecosystem engagement with the millimeter wave?
Yeah, I mean, we are aware that like our partners and members have done some interoperability between the PHY and the Layer 2/3 stack. So those solutions using the Small Cell Forum FAPI interface exist. Obviously, Small Cell Forum have also defined the P19 spec, and Jack Rose has talked about implementation of that in the TMYTEK solution, and certainly Picocom support that P19 spec both on FR1, but also it will be on FR2 as well. So I think the Small Cell Forum have enabled IoT to be more straightforward and agnostic by the FAPI interfaces, and there's been a lot of work particularly member Qualcomm, around the definition of those standards. So and also the stack vendor Radisys as well.
And, yes, absolutely. I was going to, and actually it's giving me ideas for another webinar spinning off from this. So I might come back to that one, because I think there was some quite interesting thoughts that came from David around the economics of the smaller networks that utilize millimeter wave, and there's clearly some optimization that can happen around the size of the arrays and the deployment and optimizing the power and the beam steering algorithms. A lot of opportunity for differentiation in product lines and things, which is quite an interesting area, I think, to explore. Okay, I'm going to call it a day there, because we're spot on time. I just want to thank our presenters for a fantastic run through on the millimeter wave. Thank you very much, everyone on the panel. Thank you for those who you are online and have sent in some questions. The material will be available on the SCF website. I encourage you also to download the report that Vicky was talking about at the start of the webinar. And we will have another webinar from the SCF, likely, I think, to be on the topic of market trends, as we did last year at a similar time last year. So thank you everyone for connecting, and look forward to connecting again in the future for the next of the SCF webinars.
Thank you.
Thank you.
Thank you.